Windows Server. The Microsoft Windows 7 operating system is a 32 and 64-bit preemptive multitasking client operating system for microprocessors, implementing the Intel IA32 and AMD 64 instruction set architectures (ISAs). Microsoft's corresponding server operating system, Windows Server 2008 R2, is based on the same code as Windows 7 but supports only the 64-bit AMD 64 and IA64 Itanium ISAs. Windows 7 is the latest in a series of Microsoft operating systems based on its NT code, which replaced the earlier systems based on Windows 95-98. In this chapter, we discuss the key goals of Windows 7, the layered architecture of the system that has made it so easy to use, the file system, the networking features, and the programming interface. History. In the mid-1980s, Microsoft and IBM cooperated to develop the OS/2 operating system, which was written in assembly language for single-processor Intel 80286 systems. In 1988, Microsoft decided to end the joint effort with IBM and develop its own New Technology or NT portable operating system to support both the OS/2 and POSIX application programming interfaces (APIs). In October 1988, Dave Cutler, the architect of the DEC VAX VMS operating system, was hired and given the charter of building Microsoft's new operating system. Originally, the team planned to use the OS/2 API as NT's native environment, but during development, NT was changed to use a new 32-bit Windows API called Win32, based on the popular 16-bit API used in Windows 3.0. The first versions of NT were Windows NT 3.1 and Windows NT 3.1 Advanced Server. At that time, 16-bit Windows was at version 3.1. Windows NT version 4.0 adopted the Windows 95 user interface and incorporated Internet Web Server and web browser software. In addition, user interface routines and all graphics code were removed into the kernel to improve performance with the side effect of decreased system reliability. Although previous versions of NT had been ported to other microprocessor architectures, the Windows 2000 version, released in February 2000, supported only Intel and compatible processors due to marketplace factors. Windows 2000 incorporated significant changes. It added Active Directory and X.500 base directory service, better networking and laptop support, support for plug-and-play devices, a distributed file system, and support for more processors and more memory. In October 2001, Windows XP was released as both an update to the Windows 2000 desktop operating system and a replacement for Windows 95-98. In 2002, the server edition of Windows XP became available, called Windows.NET Server. Windows XP updated the graphical user interface (GUI) with a visual design that took advantage of more recent hardware advances and many new ease-of-use features. Numerous features were added to automatically repair problems in applications and the operating system itself. As a result of these changes, Windows XP provided better networking and device experience, including zero configuration wireless, instant messaging, streaming media, and digital photography, video, dramatic performance improvements for both the desktop and large multiprocessors, and better reliability and security than earlier Windows operating systems. The result was Windows 7, which was released in October 2009 along with corresponding server editions of Windows. Among the significant engineering changes in the increased use of executing tracing rather than counters or profiling to analyze system behavior. Tracing runs constantly in the system, watching hundreds of scenarios execute. When one of these scenarios fails, or when it succeeds but does not perform well, the traces can be analyzed to determine the cause. Windows 7 uses a client-server architecture like MASH to implement two operating system personalities, Win32 and POSIX, with user-level processes called subsystems. At one time, Windows also supported an OS2 subsystem, but it was removed in Windows XP due to the demise of OS2. The subsystem architecture allows enhancements to be made to one operating system personality without affecting the application compatibility of the other. Although the POSIX subsystem continues to be available for Windows 7, the Win32 API has become very popular and the POSIX APIs are used by only a few sites. Windows 7. Windows 7 is a multi-user operating system supporting simultaneous access through distributed services or through multiple instances of the GUI via the Windows Terminal services. The server editions of Windows 7 support simultaneous terminal server sessions from Windows desktop systems. The desktop editions of Terminal Server multiplex the keyboard, mouse, and monitor between virtual terminal sessions for each logged-on user. This feature, called fast user switching, allows users to preempt each other at the console of a PC without having to log off and log on. We noted earlier that some GUI implementation moved into kernel mode in Windows NT 4.0. It started to move into user mode again with Windows Vista, which included the Desktop Window Manager DWM as a user mode process. DWM implements the desktop compositing of Windows, providing the Windows Aero interface look on top of the Windows DirectX graphics software. DirectX continues to run in the kernel, as does the code implementing Windows' previous windowing and graphics models Win32K and GDI. Windows 7 made substantial changes to the DWM, significantly reducing its memory footprint and improving its performance. Windows XP. It was the first version of Windows to ship a 64-bit version for the IA64 in 2001 and the AMD 64 in 2005. Internally, the native NT file system, NTFS, and many of the Win32 APIs have always used 64-bit integers where appropriate, so the major extension to 64-bit in Windows XP was supported for large virtual addresses. However, 64-bit editions of Windows also support much larger physical memories. By the time Windows 7 shipped, the AMD 64 ISA had become available on almost all CPUs from both Intel and AMD. In addition, by that time, physical memories on client systems frequently exceeded the 4 GB limit of the IA32. As a result, the 64-bit version of Windows 7 is now commonly installed on larger client systems. Because of the AMD 64 architecture supports high-fidelity IA32 compatibility at the level of individual processors, 32 and 64-bit applications can be freely mixed in a single system. In the rest of our description of Windows 7, we will not distinguish between the client editions of Windows 7 and the corresponding server editions. They are based on the same core components and run the same binary files for the kernel and most drivers. Similarly, although Microsoft ships a variety of different editions of each release to address different market price points, few of the differences between editions are reflected in the core of the system. Design principles. Microsoft's design goals for Windows included security, reliability, Windows and POSIX application compatibility, high performance, extensibility, portability, and international support. Some additional goals, energy efficiency and dynamic device support, have recently been added to this list. Windows 7 security goals required more than just adherence to the design standards that had enabled Windows NT 4.0 to receive a C2 security classification from the US government. Classification signifies a moderate level of protection from defective software and malicious attacks. Classifications were defined by the Department of Defense Trusted Computer System Evaluation Criteria, also known as the Orange Book. Extensive code review and testing were combined with sophisticated automatic analysis tools to identify and investigate potential defects that might represent security vulnerabilities. Windows bases security on discretionary access controls. System objects including files, registry settings, and kernel objects are protected by access control lists, ACLs. ACLs are vulnerable to user and programmer errors, as well as to the most common attacks on consumer systems in which the user is tricked into running code, often while browsing the web. Windows 7 includes a mechanism called integrity levels that acts as a rudimentary capability system for controlling access. Objects and processes are marked as having low, medium, or high integrity. Windows does not allow a process to modify an object with a higher integrity level, no matter what the setting of the ACL. Other security measures include address space layout randomization, ASLR, non-executable stacks and heaps, and encryption and digital signature facilities. ASLR thwarts many forms of attack by preventing small amounts of injected code from jumping easily to code that is already loaded in a process as part of normal operation. This safeguard makes it likely that a system under attack will fail or crash rather than let the attacking code take control. Recent chips from both Intel and AMD are based on the AMD 64 architecture, which allows memory pages to be marked so that they cannot contain executable instruction code. Windows tries to mark stacks and memory heaps so that they cannot be used to execute code, thus preventing attacks in which a program bug allows a buffer to overflow and then is tricked into executing the contents of the buffer. This technique cannot be applied to all programs because some rely on modifying data and executing it. A column labeled Data Execution Prevention in the Windows Task Manager shows which processes are marked to prevent these attacks. System components. The main layers of the HAL, the kernel, and the executive, all of which run in kernel mode, and a collection of subsystems and services that run in user mode. The user mode subsystems fall into two categories: the environmental subsystems, which emulate different operating systems, and the protection subsystems, which provide security functions. One of the chief advantages of this type of architecture is that interactions between modules are kept simple. The remainder of this section describes these layers and subsystems. Hardware abstraction layer. The HAL is the layer of software that hides hardware chipset differences from upper levels of the operating system. The HAL exports a virtual hardware interface that is used by the kernel dispatcher, the executive, and the device drivers. Only a single version of each device driver is required for each CPU architecture, no matter what support chips might be present. Device drivers map devices and access them directly, but the chipset's specific details of mapping memory, configuring I/O buses, setting up DMA, and copying with other board-specific facilities are all provided by the HAL interfaces. Kernel. The kernel layer of Windows has four main responsibilities: thread scheduling, low-level processor synchronization, interrupt and exception handling, and switching between user mode and kernel mode. The kernel is implemented in the C language, using assembly language only where absolutely necessary to interface with the lowest level of the hardware architecture. The kernel is organized according to object-oriented design principles. An object type in Windows is a system-defined data type that has a set of attributes, data values, and a set of methods, for example, functions or operations. An object is an instance of an object type. The kernel performs its job by using a set of kernel objects whose attributes store the kernel data and whose methods perform the kernel activities. Kernel dispatcher. The kernel dispatcher provides the foundation for the executive and the subsystems. Most of the dispatcher is never paged out of memory and its execution is never preempted. Its main responsibilities are thread scheduling and context switching, implementation of synchronization primitives, timer management, software interrupts, asynchronous and deferred procedure calls, and exception dispatching. Threads and scheduling. Like many other modern operating systems, Windows uses processes and threads for executable code. Each process has one or more threads, and each thread has its own scheduling state, including actual priority, processor affinity, and CPU usage information. There are 6 thread states: ready, standby, running, waiting, transition, and terminated. Ready indicates that the thread is waiting to run. The highest priority ready thread is moved to the standby state, which means it is the next thread to run. In a multiprocessor system, each processor keeps one thread in a standby state. A thread is running when it is executing on a processor. It runs until it is preempted by a higher priority thread, until it terminates, until its allotted execution time quantum ends, or until it waits on a dispatcher object such as an event signaling I/O completion. A thread is in the waiting state when it is waiting for a dispatcher object to be signaled. A thread is in the transition state while it waits for resources necessary for execution. For example, it may be waiting for its kernel stack to be swapped in from disk. A thread enters the terminated state when it finishes execution. Implementation of synchronization primitives. Key operating system data structures are managed as objects using common facilities for location, reference counting, and security. Dispatcher objects control dispatching and synchronization in the system. Example of these objects include the following. The event object is used to record an event occurrence and to synchronize this occurrence with some action. Notification events signal all waiting threads, and synchronization events signal a single waiting thread. The mutant provides kernel mode or user mode mutual exclusion associated with the notion of ownership. The mutex, available only in kernel mode, provides deadlock-free mutual exclusion. The semaphore object acts as a counter or gate to control the number of threads that access a resource. The thread object is the entity that is scheduled by the kernel dispatcher. It is associated with a process object which encapsulates a virtual address space. The thread object is signaled when the thread exits and the process object when the process exits. The timer object is used to keep track of time and to signal timeouts when operations take too long and need to be interrupted, or when a periodic activity needs to be scheduled. Many of the dispatcher objects are accessed from user mode via an open operation that returns a handle. The user mode code polls or waits on handles to synchronize with other threads as well as with the operating system. Software interrupts. Asynchronous and deferred procedure calls. The dispatcher implements 2 types of software interrupts: asynchronous procedure calls, APCs, and deferred procedure calls, DPCs, mentioned earlier. An asynchronous procedure call breaks into an executing thread and calls a procedure. APCs are used to begin execution of new threads, suspend or resume existing threads, terminate threads or processes, deliver notification that an asynchronous I/O has completed, and extract the contents of the CPU registers from a running thread. APCs are queued to specific threads and allow the system to execute both system and user code within a processor's context. User mode execution of an APC cannot occur at arbitrary times, but only when the thread is waiting in the kernel and marked alertable. Exceptions and interrupts. The kernel dispatcher also provides trap handling for exceptions and interrupts generated by hardware or software. Windows defines several architecture-independent exceptions, including memory access violation, integer overflow, floating point overflow or underflow, integer divide by zero, floating point divide by zero, illegal instruction, data misalignment, privilege instruction, page read error, access violation, paging file quota exceeded, debugger breakpoint, debugger single step. The trap handlers deal with simple exceptions. Elaborate exception handling is performed by the kernel's exception dispatcher. The exception dispatcher creates an exception record containing the reason for the exception and finds an exception handler to deal with it. When an exception occurs in kernel mode, the exception dispatcher simply calls a routine to locate the exception handler. If no handler is found, a fatal system error occurs and the user is left with the infamous blue screen of death that signifies system failure. Exception handling is more complex for user mode processes because an environmental subsystem such as POSIX system sets up a debugger port and an exception port for every process it creates. If a debugger port is registered, the exception handler sends the exception to the port. If the debugger port is not found or does not handle that exception, the dispatcher attempts to find an appropriate exception handler. If no handler is found, the debugger is called again to catch the error for debugging. If no debugger is running, a message is sent to the process's exception port to give the environmental subsystem a chance to translate the exception. For example, the POSIX environment translates Windows exception messages into POSIX signals before sending them to the thread that caused the exception. Finally, if nothing else works, the kernel simply terminates the process containing the thread that caused the exception. Executive. The Windows Executive provides a set of services that all environmental subsystems use. The services are grouped as follows: Object Manager, Virtual Memory Manager, Process Manager, Advanced Local Procedure Call Facility, I/O Manager, Cache Manager, Security Reference Monitor, Plug and Play and Power Managers, Registry and Booting. Object Manager. For managing kernel mode entities, Windows uses a generic set of interfaces that are manipulated by user mode programs. Windows calls these entities objects, and the executive component that manipulates them is the Object Manager. Examples of objects are semaphores, mutexes, events, processes, and threads. All these are dispatcher objects. Threads can block in the kernel dispatcher waiting for any of these objects to be signaled. The process, thread, and virtual memory APIs use process and thread handles to identify the process or thread to be operated on. Other examples of objects include files, sections, ports, and various internal I/O objects. File objects are used to maintain the open state of files and devices. Sections are used to map files. Local communication endpoints are implemented as port objects. User mode code accesses these objects using an opaque value called a handle, which is returned by many APIs. Each process has a handle table containing entries that track the objects used by the process. The system process, which contains the kernel, has its own handle table which is protected from user code. The handle tables in Windows are represented by a tree structure which can expand from holding 1024 handles to holding over 16 million. Kernel mode code can access an object by using either a handle or a reference pointer. Virtual Memory Manager. The executive component that manages the virtual address space, physical memory allocation, and paging is the Virtual Memory VM Manager. The design of the VM Manager assumes that the underlying hardware supports virtual to physical mapping, a paging mechanism, and transparent cache coherence on multiprocessor systems, as well as allowing multiple page table entries to map to the same physical page frame. The VM Manager in Windows uses a page-based management scheme with page sizes of 4 KB and 2 MB on AMD 64 and IA32 compatible processors and 8 KB on the IA64. Pages of data allocated to a process that are not in physical memory are either stored in the paging files on disk or mapped directly to a regular file on a local or remote file system. A page can also be marked zero fill on demand, which initializes the page with zeros before it is allocated, thus erasing the previous contents. Key areas of the kernel mode region that are not identical for all processes are the self-map, hyperspace, and session space. The hardware references a processor's page table using physical page frame numbers, and the page table self-map makes the contents of the processor's page table accessible using virtual addresses. Hyperspace maps the current processor's working set information into the kernel mode address space. Session space is used to share an instance of the Win32 and other session-specific drivers among all the processes in the same terminal server TS session. Different TS sessions share different instances of these drivers, yet they are mapped at the same virtual addresses. The lower user mode region of virtual address space is specified to each process and accessible by both user and kernel mode threads. Let's look closely at the last two of these protection settings. A no-access page raises an exception if accessed. The exception can be used, for example, to check whether a faulty program iterates beyond the end of an array, or simply to detect that the program attempted to access virtual addresses that are not committed to memory. User and kernel mode stacks use no-access pages as guard pages to detect stack overflows. Another use is to look for heap buffers overruns. Both the user mode memory allocator and the special kernel allocator used by the device verifier can be configured to map each allocation onto the end of a page, followed by a no-access page to detect programming errors that access beyond the end of an allocation. The copy-on-write mechanism enables the VM Manager to use physical memory more efficiently. When two processors want independent copies of data from the same section object, the VM Manager places a single shared copy into virtual memory and activates the copy-on-write property for that region of memory. If one of the processors tries to modify data in a copy-on-write page, the VM Manager makes a private copy of the page for the process. A page table layout is shown below. The virtual address translation in Windows uses a multi-level page table. For IA32 and AMD 64 processors, each process has a page directory that contains 512 page directory entries PDEs, 8 bytes in size. Each PDE points to a PTE table that contains 512 page table entries PTEs, 8 bytes in size. Each PTE points to a 4 KB page frame in physical memory. For a variety of reasons, the hardware requires that the page directories or PTE tables at each level of a multi-level page table occupy a single page. Thus, the number of PDEs or PTEs that fit in a page determine how many virtual addresses are translated by that page. I/O Manager. The I/O Manager is responsible for managing file systems, device drivers, and network drivers. It keeps track of which device drivers, filter drivers, and file systems are loaded, and it also manages buffer for I/O requests. It works with the VM Manager to provide memory-mapped file I/O and controls the Windows Cache Manager, which handles caching for the entire I/O system. The I/O Manager is fundamentally asynchronous, providing synchronous I/O by explicitly waiting for an I/O operation to complete. The I/O Manager provides several models of asynchronous I/O completion, including setting of events, updating of a status variable in the calling process, delivery of APCs to initiating threads, and use of I/O completion ports, which allow a single thread to process I/O completions from many other threads. Device drivers are arranged in a list for each device called a driver or I/O stack. A driver is represented in the system as a driver object. Because a single driver can operate on multiple devices, the drivers are represented in the I/O stack by a device object, which contains a link to the driver object. The I/O Manager converts requests it receives into a standard form called an I/O request packet (IRP). It then forwards the IRP to the first driver in the targeted I/O stack for processing. After a driver processes the IRP, it calls the I/O Manager either to forwarding the IRP to the next driver in the stack or, if all processing is finished, to complete the operation presented by IRP. The I/O request may be completed in a context different from the one in which it was made. For example, if a driver is performing its part of an I/O operation and is forced to block for an extended time, it may queue the IRP to a worker thread to continue processing in the system context. In the original thread, the driver returns a status indicating that the I/O request is pending so that the thread can continue executing in parallel with the I/O operation. An IRP may also be processed in interrupt service routines and completed in an arbitrary process context. Because some final processing may need to take place in the context that initiated the I/O Manager uses an APC to do final I/O completion processing in the process context of the originating thread. Terminal services and fast user switching. Windows supports a GUI-based console that interfaces with the user via keyboard, mouse, and display. Most systems also support audio and video. Audio input is used by Windows voice recognition software. Voice recognition makes the system more convenient and increases its accessibility for users with disabilities. Windows 7 added support for multi-touch hardware, allowing users to input data by touching the screen and making gestures with one or more fingers. Eventually, the video input capability, which is currently used for communication applications, is likely to be used for visually interpreting gestures, as Microsoft has demonstrated for its Xbox 360 Kinect product. Other future input experiences may evolve from Microsoft's Surface computer, most often installed at public venues such as hotels and conference centers. The Surface computer is a table surface with special cameras underneath. It can track the actions of multiple users at once and recognize objects that are placed on top. The PC was, of course, envisioned as a personal computer, an inherently single-user machine. Modern Windows, however, supports the sharing of a PC among multiple users. Each user that is logged on using the GUI has a session created to represent the GUI environment he will be using and to contain all the processes created to run his applications. Windows allows multiple sessions to exist at the same time on a single machine. However, Windows only supports a single console consisting of all the monitors, keyboards and mice connected to the PC. Only one session can be connected to the console at a time. From the login screen displayed on the console, users can create new sessions or attach to an existing session that was previously created. This allows multiple users to share a single PC without having to log off and on between users. Microsoft calls this use of sessions fast user switching. File system. The native file system in Windows is NTFS. It is used for all local volumes. However, associated USB thumb drives, flash memory on cameras, and external disks may be formatted with the 32-bit FAT file system for portability. FAT is a much older file system format that is understood by many systems besides Windows, such as the software running on cameras. A disadvantage is that the FAT file system does not restrict file access to authorized users. The only solution for securing data with FAT is to run an application to encrypt the data before storing it on the file system. In contrast, NTFS uses ACLs to control access to individual files and support implicit encryption of individual files or entire volumes using Windows BitLocker feature. NTFS implements many other features as well, including data recovery, fault tolerance, very large files and file systems, multiple data streams, Unicode names, sparse files, journaling, volume shadow copies, and file compression. NTFS internal layout. The fundamental entity in NTFS is a volume. A volume is created by the Windows Logical Disk Management utility and is based on a logical disk partition. A volume may occupy a portion of a disk or an entire disk or may span several disks. NTFS does not deal with individual sectors of a disk, but instead uses clusters as the units of disk allocation. A cluster is a number of disk sectors that is a power of 2. The cluster size is configured when an NTFS file system is formatted. The default cluster size is based on the volume size, 4 KB for volumes larger than 2 GB. Given the size of today's disks, it may make sense to use cluster sizes larger than the Windows defaults to achieve better performance, although these performance gains will come at the expense of more internal fragmentation. NTFS uses logical cluster numbers LCNs as disk addresses. It assigns them by numbering clusters from the beginning of the disk to the end. Using this scheme, the system can calculate a physical disk offset in bytes by multiplying the LCN by the cluster size. A file in NTFS is not a simple byte stream as it is in Unix. Rather, it is a structured object consisting of typed attributes. Each attribute of a file is an independent byte stream that can be created, deleted, read, and written. Some attribute type for all files, including the file name or names if the file has aliases, such as an MS-DOS short name, the creation time, and the security descriptor that specifies the access control list. User data are stored in data attributes. NTFS metadata. The NTFS volumes metadata are all stored in files. The first file is the MFT. The second file, which is used during recovery if the MFT is damaged, contains a copy of the first 16 entries of the MFT. The next few files are also special in purpose. They include the files described below. The log file records all metadata updates to the file system. The volume file contains the name of the volume, the version of NTFS that formatted the volume, and a bit that tells whether the volume may have been corrupted and needs to be checked for consistency using the CheckDisk program. The attribute definition table indicates which attribute types are used in the volume and what operations can be performed on each of them. The root directory is the top-level directory in the file system hierarchy. The bitmap file indicates which clusters on a volume are allocated to files and which are free. The boot file contains the startup code for Windows and must be located at a particular disk address so that it can be found easily by a simple ROM bootstrap loader. The boot file also contains the physical address of the MFT. The bad cluster file keeps track of any bad areas on the volume. NTFS uses this record for error recovery. Security. The security of an NTFS volume is derived from the Windows Object Model. Each NTFS file references a security descriptor which specifies the owner of the file and an access control list which contains the access permissions granted or denied to each user or group listed. Early versions of NTFS used a separate security descriptor as an attribute of each file. Beginning with Windows 2000, the security descriptor's attribute points to a shared copy with a significant savings in disk and caching space. Many files have identical security descriptors. In normal operation, NTFS does not enforce permissions on traversal of directories in file path names. However, for compatibility with POSIX, these checks can be enabled. Traversal checks are inherently more expensive since modern parsing of file path names uses prefix matching rather than directory by directory parsing of path names. Prefix matching is an algorithm that looks up strings in a cache and finds the entry with the longest match. For example, an entry for /FOO/bar/dir would be a match for /FOO/dir2/dir3/myfile. The prefix matching cache allows path name traversal to begin much deeper in the tree, saving many steps. Enforcing traversal checks means that the user's access must be checked at each directory level. For instance, a user might lack permission to traverse /FOO/bar, so starting at the access for /FOO/bar/dir would be an error. Networking. Windows supports both peer-to-peer and client-server networking. It also has facilities for network management. The networking components in Windows provides data transport, inter-process communication, file sharing across a network, and the ability to send print job printers. Network interfaces. To describe networking in Windows, we must first mention two of the internal networking interfaces, the Network Device Interface Specification (NDIS) and the Transport Driver Interface (TDI). The NDIS interface was developed in 1989 by Microsoft and 3Com to separate network adapters from transport protocols so that either could be changed without affecting the other. NDIS resides at the interface between the data link and network layers in the ISO model and enables many protocols to operate over many different network adapters. In terms of the ISO model, the TDI is the interface between the transport layer, layer 4, and the session layer, layer 5. This interface enables any session layer component to use any available transport mechanism. Similar reasoning led to the streams mechanism in Unix. The TDI supports both connection-based and connection-less transport and has functions to send any type of data. Protocols. Windows implements transport protocols as drivers. These drivers can be loaded and unloaded from the system dynamically, although in practice the system typically has to be rebooted after a change. Windows comes with several networking protocols. Next, we discuss a number of these protocols. Server Message Block. The Server Message Block SMB protocol was first introduced in MS-DOS 3.1. The system uses the protocol to send I/O requests over the network. The SMB protocol has 4 message types. Session control messages are commands that start and end a redirector connection to a shared resource at the server. A redirector uses file messages to access file at the server. Printer messages are used to send data to a remote print queue and to receive status information from the queue, and messages are used to communicate with another workstation. A version of the SMB protocol was published as the Common Internet File System (CIFS) and is supported on a number of operating systems. Transmission Control Protocol, Internet Protocol. The Transmission Control Protocol, Internet Protocol, TCP/IP suite that is used on the Internet has become the de facto standard networking infrastructure. Windows uses TCP/IP to connect to a wide variety of operating systems and hardware platforms. The Windows TCP/IP package includes the Simple Network Management Protocol (SNM), the Dynamic Host Configuration Protocol (DHCP), and the older Windows Internet Name Service (WINS). Windows Vista introduced a new implementation of TCP/IP that supports both IPv4 and IPv6 in the same network stack. This new implementation also supports offloading of the network stack onto advanced hardware to achieve very high performance for servers. Windows provides a software firewall that limits the TCP ports that can be used by programs for network communication. Network firewalls are commonly implemented in routers and are a very important security measure. Having a firewall built into the operating system makes a hardware router unnecessary, and it also provides a more integrated management and easier use. Point-to-Point Tunneling Protocol. The Point-to-Point Tunneling Protocol, PPTP, is a protocol provided by Windows to communicate between remote access server modules running on Windows Server machines and other client systems that are connected over the Internet. The remote access servers can encrypt data sent over the connection, and they support multi-protocol virtual private networks (VPNs) over the Internet. HTTP Protocol. The HTTP protocol is used to put information using the World Wide Web. Windows implements HTTP using a kernel mode driver, so web servers can operate with a low overhead connection to the networking stack. HTTP is a fairly general protocol which Windows makes available as a transport option for implementing RPC. Web Distributed Authoring and Versioning Protocol. Web Distributed Authoring and Versioning (WebDAV) is an HTTP-based protocol for collaborative authoring across a network. Windows builds a WebDAV redirector into the file system. Being built directly into the file system enables WebDAV to work with other file system features such as encryption. Personal files can then be stored securely in a public place. Because WebDAV uses HTTP, which is a get-put protocol, Windows has to cache the files locally so programs can use read and write operations on parts of the files. Named pipes. Named pipes are a connection-oriented messaging mechanism. A process can use name pipes to communicate with other processes on the same machine. Since name pipes are accessed through the file system interface, the security mechanisms used for file objects also apply to named pipes. The SMB protocol supports named pipes, so named pipes can also be used for communication between processes on different systems. The format of pipe names follows the Uniform Naming Convention (UNC). A UNC name looks like a typical remote file name. The format is // server name / share name /x /y /z, where server name identifies a server on the network, share name identifies any resource that is made available to network users, such as directories, files, named pipes and printers, and /x /y /z is a normal file path name. Remote procedure calls. A remote procedure call, RPC, is a client-server mechanism that enables an application on one machine to make a procedure call to code on another machine. The client calls a local procedure a stub routine that packs its arguments into a message and sends them across the network to a particular server process. The client-side stub routine then blocks. Meanwhile, the server unpacks the message, calls the procedure, packs the return results into a message and sends them back to the client stub. The client stub unblocks, receives the message, unpacks the results of the RPC and returns them to the caller. This packing of arguments is sometimes called marshalling. The client stub code and the descriptors necessary to pack and unpack the arguments for an RPC are compiled from a specification written in the Microsoft Interface Definition language. Programmer Interface. The Win32 API is the fundamental interface to the capabilities of Windows. This section describes 5 main aspects of the Win32 API: access to kernel objects, sharing of objects between processes, process management, inter-process communication, and memory management. Access to kernel objects. The Windows kernel provides many services that application programs can use. Application programs obtain these services by manipulating kernel objects. A process gains access to a kernel object named XXX by calling the createXXX function to open a handle to an instance of XXX. This handle is unique to the process. Depending on which object is being opened, if the create function fails, it may return 0 or it may return a special constant named invalid handle value. A process can close any handle by calling the close handle function, and the system may delete the object if the count of handles referencing the object in all processes drops to 0. Sharing objects between processes. Windows provides 3 ways to share objects between processes. The first way is for a child process to inherit a handle to the object. When the parent calls the createXXX function, the parent supplies a securities attribute structure with the bInherit handle field set to true. This field creates an inheritable handle. Next, the child process is created, passing a value of true to the create process function's bInherit handle argument. Assuming the child process knows which handles are shared, the parent and child can achieve inter-process communication through the shared objects. The child process gets the value of the handle from the first command line argument and then shares the semaphore with the parent process. The second way to share objects is for one process to give the object a name when the object is created and for the second process to open the name. This method has 2 drawbacks. Windows does not provide a way to check whether an object with the chosen name already exists, and the object namespace is global without regard to the object type. For instance, 2 applications may create and share a single object named foo when 2 distinct objects, possibly by different types, were desired. Summary. Microsoft designed Windows to be an extensible, portable operating system, one able to take advantage of new techniques and hardware. Windows supports multiple operating environments and symmetric multiprocessing, including both 32-bit and 64-bit processors and NUMA computers. The use of kernel objects to provide basic services along with support for client-server computing enables Windows to support a wide variety of application environments. Windows provides virtual memory, integrated caching, and preemptive scheduling. It supports elaborate security mechanisms and includes internalization features. Windows runs on a wide variety of computers, so users can choose and upgrade hardware to match their budgets and performance requirements without needing to alter the application.